Okay, let's start. Hello, everyone. My name is Morha Fares, and I'm a PhD fellow at the Language Technology Group. So I'll be teaching this course for about 4 to 6 lectures from now on. And after the Lisp introduction that Stefan gave over the past few weeks, we're now ready to move to more to different new topics that are related to machine learning and natural language processing. And today's topic is going to be about semantic spaces. And since I'm not as experienced as Stefan in handling uncomfortable silences, I'll start with asking a question, just facing my fears. And the question is really simple. How many of you know the meaning of the word Alcazar? Okay, so if I show you these sentences now, so the Alcazar did not become a permanent residence for the royal family until 1905. The Alcazar was built in the 10th century. You can also visit the Alcazar while the royal family is there. Can you guess what could Alcazar be? Castle? Yes, more or less. So it's a palace. So this is a Spanish word for the palaces, the royal palaces that were built in the Moorish style. And the idea here is that you could actually guess the meaning of that word, even though you actually didn't know it, because you saw it within a context. And that's what we will be talking about today, is how do we learn the meaning of words based on the context they occur in. And so we will be asking a question, can a program reuse the same intuition that you just used to automatically learn word meanings? And that could be done by simply looking at large amounts of data, textual data, and without prior knowledge about the meaning of the words. And this is a very important, and this is what we call, by the way, vector space semantics. And this method has been very hot in NLP research in general, and it has proved successful for so many reasons. But most importantly, it's because learning the meaning of words, semantics, is very essential to many applications. So search engines, which you always use all the time, needs to know the meaning of words in order to return meaningful results for you. And the fact that you can actually learn meanings of words without having to manually annotate data is very appealing aspect of this model, because manual annotation of data is a very expensive process. And so we will discuss how can we actually represent word meaning in a well-defined mathematical model. And so based on these two sort of questions, the concepts we will introduce today, first is what's distributional semantics, and then what are vector spaces, and then when we put distributional semantics together with vector spaces, we arrive at what's called semantic spaces. So what we just used, the concept that we just discussed, is called distributional hypothesis, or also known as the contextual theory of meaning. And this hypothesis takes root in linguistics and philosophy of language. And probably the most famous quote here is, "You shall know a word by the company it keeps," by Firth in 1957. And the idea is that you can learn the meanings of words by the other, or so not learn, but the meanings of words is constrained by the other words that they occur with. And so, for example, if you think of a verb like eat, you can't use, or generally speaking, you can't use direct object of eat that is something that's not edible, right? So when you start saying the verb eat, then you would expect to get an object that's edible, and the same applies to drink. So the idea here is that whenever words come together in a linguistic construction, they impose constraint on each other, and that's what we call contextual meaning, in a sense. So of course one can argue that you can actually put words together and you still have a fully grammatical sentence. This is the famous example by Chomsky: colorless green ideas sleep furiously. So this doesn't make any sense in terms of semantics, but it's a fully grammatical sentence. But when we start thinking about semantics, we see that you can't you can't talk about sleeping with ideas, right? So this is the core idea behind the concept of distributional semantics, or the distributional hypothesis in general. And when we talk about distributional here, we don't mean distributional in the probabilistic sense. We mean distributional as in the context in which words appear in. And so if we rephrase our hypothesis, we end up with something like this. If two words share similar context, we can assume that they have similar meanings. And so the problem of comparing meanings become a problem of comparing context. And that doesn't require any prior knowledge on our side. And again, our goal is to automatically learn word semantics based on this hypothesis. So what's distributional semantics in practice? How can we put that hypothesis in practice if you want to implement it in a machine learning natural language processing? The idea is that we have a set of words in our vocabulary, V, and we want to record the context of these words across a large collection of text. And this collection of text we will refer to always as corpus. And each word would be represented by a set of contextual features. Each one of these features is observing something about the context. So the feature could be the word that's just next to our target word. We will come into details to all of these points, but just an overview of what to expect. And then words that are found to have similar features are also expected to have similar meanings. So if we look again at our hypothesis, we say if two words share similar context, we can assume that they share similar meanings. So what do we mean by word, context, and similar? These are things that we need to agree on before we start looking at the actual vector space model. So what's a word? So here I will present a collection of pre-processing tasks or pre-processing methods that are usually applied to the raw text that we usually see. And one of the very first step is tokenization. This is something you have already seen in assignment 1, right? So you have implemented, or at least you have looked at an implementation of a tokenization function. And the idea is that we have a string of characters, and we want to split that string into meaningful units, right? And in English, that sort of what we provided you with was a tokenizer that splits on white space, because that's the clear delimiter between it's a clear word boundary. But then we asked, how could we refine this tokenizer? What are the problems with this criterion of splitting only on white space and not thinking of anything else? And since you have answered this question, I guess, so you can give me some suggestions. Yeah. 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 Yeah, that's a very good observation. So one thing is as we just heard is punctuations. So how do we deal with these? But there are other things also. So apostrophes, contractions like didn't and couldn't. What do we do about these? Do we split couldn't as could and n apostrophe t, or what do we do about this? These are design decisions. It's not complicated, but these are design decisions that we want to agree on. And you will see different implementations of different tokenizers. And then we come to words like New York, and then you can start this discussion. What's a word? We're not going to start this discussion, but you can keep in mind that there are also things called multi-word expressions or units like New York, which make sense to keep as one word for some applications. So if we tokenize this sentence, we end up with the following tokens, as you can see. And this is the very first step. So we want to further normalize this text. And one step is to downcase. That's also something you will do in exercise 2a. So you downcase all words. And one thing you can also do is to replace all numerals with a special character or a special word. So we don't care whether the number is 50 or 100 or 20. What matters to us is this is a number. So we can replace all numbers by a special word. And you will see later on why we want to keep the number of words as small as possible, while of course preserving the content. And we can go one level more than this. So we can apply two things. One is called lemmatization and the other is called stemming. That will be applied on the tokens here. So lemmatization basically can be defined as stripping away the inflectional affixes, if you want, of words, or sort of affixes, prefixes, and suffixes. So if you look at a word like programs here, this is a noun and the plural form, right? So but the original noun or the singular form is program, and it was inflected with this s here, so which is the plural marker in English, and we want that to be transformed back into a simpler sort of form, so that we don't consider programs and program as two separate tokens. We want them to be the same. And the same could be done also with verbs. So we could transfer from past tense to present, etc. And another step that could be done, which is stemming, which is sometimes sort of blurred with lemmatization, but they are not the same. So stemming is concerned with more sort of derivational aspects of morphology, if you want. So a word like programmer is a noun that was derived from the verb program, right? So we added er in the end. And this is also one effect that we want to take away, so that we have a smaller number of words. So again, we can apply stemming, and sort of stemming gives us the stem, the root of the word. And so now our sentence looks like this. I skipped over this part because these sort of tokenization, lemmatization, stemming are working on the tokens, but stop words will be filtering out some tokens. So what is stop word, or what's the function word? So the idea with removing stop words is that there are some words in English or all languages that belong to so-called closed classes. So these are words like pronouns, for example, prepositions, definitive articles. There is a limited number of pronouns and predefined. You can't just come up with a new pronoun and say this is a pronoun that I want to use. No, we know that there is a closed set of these, and they usually tend not to provide a meaningful sort of aspect for the sentence. They are functional. So if you remove them, you could still, in a way, guess what's the meaning of that word. And again, they are also what we call not discriminative feature. They're not discriminative. So a discriminative feature is something that would help you distinguish one thing from another. So say that I want to guess what laptop you have, right? So there are different types of laptops in general, and it's either Dell or MacBook. I wouldn't ask you, does your laptop have a keyboard, right? Because all laptops have keyboard, and that's the same here. So this is not a discriminative feature. I would ask you about what operating system does your laptop have, so I can guess whether it's a MacBook or it's a Dell or whatever it is. So the idea is these stop words, they don't provide the discriminative features because they occur all the time. So you see them all over the text, whatever is the context. So this is what we achieve by removing stop word removal. So these are a selection of pre-processing tasks that we normally apply in working with vector space models, but we don't need to always apply them. That's important to also realize, is that sometimes our problem will require us to keep stop words, for example, to keep pronouns. So if you think of a problem like classifying a set of documents based on whether they were authored by a single author or several authors, so then pronouns suddenly becomes a very important feature in your text, because it's if you use I or use we, then you can actually distinguish whether there were several people behind it or one person. So yeah, so this is the idea here, is that think about your problem when you apply these pre-processing tasks. One important distinction that we want to make here is the difference between token and type. So what's a token and what's a type? So type, you can think of it as a class of things, and token is instances of this class. So we have a word type called bread. There's one word type called bread, but there are many instances or tokens of this word bread. So, and what we want to achieve in this lecture is to make or to create a vector for the word type bread based on all the occurrences of the token bread. So you see the distinction here. And so how many tokens and types are there in rows is a rows is a rows is a rows? How many types are there? Yeah? Yeah. And tokens? Yeah, it would be 10. Yeah, exactly. So just aside, this is a quote by Gertrude Stein. She was an American poet and novelist, and she has this interesting way of sort of playful, repetitive way of writing poems and stories. This is very interesting to listen to on YouTube. So don't do that now, but if you want to procrastinate, you can do that later on. So yeah, so now you get the difference between what's a type and what's a token. So we now know our word. So we know that a word is defined given some criteria and pre-processing tasks. We want to define what's a context, because if you remember the hypothesis, we were talking about words having similar meanings because they have similar contexts. So say that we want to extract the context for the word bread again here, given this sentence: I bake bread for breakfast. So a context could be defined as so-called context windows. And a context window is basically n neighboring words for our target word on either side. So here we have a target word called bread, and we want to extract a context for that. So we can define a context window of, say, 5 words to the left and five words to the right, and that would be our context. In this case, if we take one only, so our context would be bake to the left and for to the right. And see here we didn't do any pre-processing. So if you had done any stop word removal, 4 would disappear, and then we'd have breakfast only. And there are many variations of this context window concept. One is distant waiting. So say that your window is 10 words to the left and 10 words to the right. So you want to include all 10 words from here on and all 10 words from here on. You might want to give more significance to words that are closer to your target word, right? So then you have a word like that occurs immediately before and a word that occurs immediately after your target word given a higher significance, and the further you move away from the target word, the lesser the lower is the significance of the words within the context. Another way of looking at context windows is n-grams. So n-gram basically says that we will look at n words at a time. So say that n here is 2, and then that's usually called bigram. So our features would be I bake together. This would be, we no longer look at one word, we look at 2 words at a time. Of course, we will come to n-grams later on in this course, but n-grams could also be done on not only on word level, it could be done on character level, and sort of K, E, K, and then K, A, and B, A, etc. Another way to define context is the so-called bag of words. So in a bag of words approach, we define context as all words occurring with our target word, but we ignore their linear ordering. So we don't care whether they occur to the right or to the left. That's not what we care about here. We just say that the word bread has these words as their context, as its context. And here we can talk about sentence level bag of words. So all words that occur with bread in the same sentence, or document level. Sort of all words in the same document. And this is what we are going to use, or you're going to implement, or maybe already implementing in exercise 2a. So this is the context we had. This is how we define context in exercise 2a. Now a bit more sophisticated, if you want, definition of context is grammatical context. So the grammatical context is defined as the grammatical relations of the target word to other words in the sentence. So the intuition here is that when we combine words together in some linguistic construction, they impose constraints on each other. So we talked about this before. So if we start with the verb like drink, we would expect its direct object to be liquid, some type of liquid, something that we can drink. And so given this intuition, we can then define features not to be the words co-occurring, but the grammatical relations that are relating our target word with the context. So here, for example, in this example, we were saying that bread is the direct object of bake. But of course, one important thing to notice here is that when you want to apply this kind of, or when we want to use this kind of grammatical context, then you assume that you actually have deeper linguistic analysis of the text. So in Bag of Words, we are working on surface form. So we look at the words and we just put them as the context. But here, we are saying that we want to look at grammatical relations, which means that we want to apply syntactic parsing maybe before we start working on this, and this adds a new layer of the kind of pre-processing that you want to do before you start. So now we have defined what's a word, we have defined what's the context. Now what's similar? So what do we mean by similar? So if you look at these two sets of words, car, road, gas, service, traffic, driver, and the other one, can you just think for a minute what's the relation that brings these words together, and what's the relation that brings this set together?
First one is things related to driving a car, and the second one is means of transportation.
Yeah, exactly. So the first set of words are words that you would expect to occur in the same sentence. So you wouldn't be surprised that car, road, and gas and service, etc., occur within the same sentence, right? And for the second set, it feels as if the meaning of these words is related, but they don't necessarily occur within the same sentence. And that's what we are trying to tell here when we talk about relatedness and sameness. So there are many ways to define this. You can talk about relatedness and sameness, or domain similarity and content similarity, or some so-called syntagmatic and paradigmatic similarity. And the idea is that the first type. So if we look at this, yeah. So these words are defined in terms of domain similarity, meaning that what matters here is that these words share the same neighborhood, or sort of they happen in the same neighborhood, in the same context. Whereas content word, they tend to substitute each other. They don't occur in the same context. But they have similar contexts. So that's here the relation is more like a so-called also positional relation. So the position of this word would be within the same sentence of these words, whereas this one is a substitution kind of relation. You can think of an easier example. So these are not directly substitutable with each other, right? But you could think of verbs like love and adore. So if you can replace one with another, and of course you can argue that this is not exactly the same, but there is some level of similarity. And so what we're saying here is in order to know which type of similarity we're talking about, we should define which context we are working with. So the type of context in our vector, or sort of, or the way we define context, will also give us clues about one of these types of semantic. And then, so when we talk about or when we have a broader definition of context, the wide context, then we were mostly referring to domain-based relatedness. This will capture domain-based relatedness. But when you have a fine-grained and linguistically informed sort of grammatical relations, for example, context, this will give you clues on the content of the words. So yeah. So now we have defined what's a word and what's a context and what's similarity. So I guess now we can agree that we have a common understanding of these concepts. So do you have any questions on this so far? Okay. So we can now move to discussing how we can exactly represent our words and context features, and how can we compare the features sort of after representing them and as vectors. So this is something we have seen before. So just to remind you, what we want to do is we want to record the context of words across a large collection of text, and we want for each word to be represented as a set of contextual features, and these features we want them to be observing or sort of measuring some observed property of the context, and words that are found to have similar features, again, will have similar meanings. So vector space model, which is the model we will be using to implement sort of word similarity, is something probably familiar to some of you. How many of you have taken this search technology course, sort of M3 800? Okay, yeah, not so many. So probably so probably not so familiar to you. So vector space models, they first appeared in IR. IR is information retrieval, which is the science behind search engines. And they appeared in the 60s, late 60s, early 70s, I think. But they are not limited. Sort of the concept of a vector space model is not limited to information retrieval. It's a general algebraic model that allows us to represent data and within sort of a very intuitive spatial metaphor, as you will see. So each data point in our data set, if you want, would be represented as a vector or a point within the space, or positioned within a coordinate system. The coordinate system is our space, and each dimension of this space is corresponds to some measurable feature or property of our objects. And to measure similarity of two objects, then what we have to do is to measure their geometrical distance, and that's where we get this spatial metaphor. So you present things in a spatial or in a geometrical sense, if you want, and then measuring similarity would be a matter of measuring distance between things or proximity between objects and features. And again, this vector representation sort of is not limited to word similarity, neither is it limited to IR. It's something that we will be using later on in machine learning methods. So what do we mean by a vector, and what do we mean by a vector space? So a vector is or the vector space is defined as a system of n dimensions, or coordinates, if you want to think of it like that, and where points are represented as real valued vectors in this space. So to give you the most basic example that most of you know, or I guess all of you know, it is this two-dimensional Euclidean plane. So it's not a space really, because it's two-dimensional, so we call it a plane. But you have all seen this, right? So I guess I can assume that at least. So and this is really what we mean by a vector space. So it's these two coordinates, so x and y, and as we talked before, these will be representing some feature that we can then take our data points and project them within this space and say that this vector v1 has a value of 5 on the x axis or the x dimension or the x feature. So these are all interchangeable now. And on y it has 5. So a vector, sort of when we say the word vector in linear algebra, we mean an ordered list of numbers. And why do we say ordered? Because each number or each element within our vector represents or the value of that vector on a specific dimension. So you cannot just write this as 8, 1 and expect this to be the same vector, right? So this is fairly basic, that 1 is on x and 8 is on y, right? So this is what we mean by vector space. Does it sound okay to all of you? It's not that difficult. The only difference, of course, is that we're not going to work with two-dimensional spaces. That's too artificially simplistic. And we were going to work with I don't know, 10,000 dimensions or even more. But what we can represent, the most we can represent in 3 dimensions, and that's what we have access to as humans. So the easy way is to look at it like that. So now what we mean by a semantic space then, given this definition of vector spaces, is really it is a vector space, but the points within this space are word, or they represent words, our target words, and the dimensions represent the context, which is, as we talked before, the context could be the 3 word to the left and the 3 word to the right, etc. So basically the context is words also here, and the distance is between the vectors in this space is the semantic represents semantic similarity. So another example, now we move to more fancy 3-dimensional kind of spaces. Here, as you can see, we name dimensions, and sort of dimensions now they present words. So these are word 1, word 2, and word 3. And T1 and T2 are 2 points in our vectors, which are 2 word types if you want. And what we show here is that the word T1 co-occurred with the contextual feature W1 2 times, and 1 time with W2 and 2 times with W3. So that's the intuition here, is that how many times T1 occurred with these features. Again, this is very simplistic. That's not what we are going to be looking at. We will be looking at so many word types and so many dimensions. So what do we mean by feature vector? So this vector here, where does it come from? So each word in our vocabulary Ti would be represented by a vector of real valued features. And our observed features should be encoded numerically, meaning that each context feature we observe, we will map to a dimension. And of course, and it will be given this index j from 1 to n. And for a given word, the value of a given feature is its number of co-occurrences for the corresponding context across our corpus. So if you think again, I bake bread for breakfast, bread would be represented by a feature of n, by a vector, of n features, and the values for this feature would be the number of co-occurrences of the word bread with each feature context or context feature. So let's take this into more concrete, sort of make this more concrete a little bit, and more formalized also. So we have a set of n features that describe the lexical context of a word Ti, and then we would have a feature vector xi, which would have normally here then we're talking about n features, then we have n elements for these features, right? And again, this n here is also, can you remember what was that again? So we said that each feature will correspond to what in our space? sort of, it's dimension, exactly. So each feature is a dimension. And it's actually here, yes. So this is a vector in n-dimensional space, and this is a word. So given a grammatical context, not a bag of word or context windows, if we assume that the ith word is bread and the jth feature is object of bake, so I here this is bread and some j here, sort of jth feature would be bake. So then this value xij equals 4, what it really means is that throughout our corpus we have observed the word bread to be the object of the verb bake. Is this clear, or should I try to sort of explain a bit more? Yeah. So which aspect you didn't? So the co-occurrence. Yeah. Let's see. Where was that? Oh, it was way back. Yeah, here. So what the sort of, we're looking at the word bread, right? So this is a word type we are interested in, and in order to encode the context features, we first define our context, right? So let's assume our context is one word to the left and one word to the right. So we go through our corpus, which is this one here, and we see that for the first instance there is within the context there is the and may. So we take these to introduce new features. So these are the features, and then we continue going through our corpus, and each time we observe this word or any other word, if we have seen it before, we increase the number of co-occurrences because we have already seen it. If we haven't seen it, then we just add it to our feature vector. Here, yeah. So this one would be, this is a feature we have already seen, right? A word context. So we just increase it by 1, and we go on. But for each new one, we would introduce a new dimension, if you want. Yeah? Do you have a question, or?
Yeah. So the dimensions is both context and each word has its own dimension.
Okay, so we talk about words as our target words. These are the feature vectors themselves, right? So this is a word like bread. So it doesn't have a dimension as a word itself that we want to represent, but its context introduced dimension. So a new word would be a new dimension if you haven't seen it before. Yes. Each new word is sort of the context is you don't have to really think about the context. What you want to think about is what are the features that we want to take into consideration to represent the meaning of our word, right? So in this case, with bread, I can probably go back to that. That's much easier. Here, so these are the dimensions, right? And this is the word itself. The word itself is a vector with an n-dimensional space. And the dimensions of this n-dimensional space is defined by the context words that we have observed. So if we have only observed 3 context words, then our dimensions would be 3. And if we, yeah.
I guess my question is all words a context word? So that when you encounter a word that you haven't seen before, do you add a dimension?
Yeah, exactly. So yes. Yeah, we can start talking about this. So now we know that our words are represented as vectors in a n-dimensional space. Again, we're back now to the 2-dimensional for simplicity. And the idea here is that we want to measure the distance between our vectors, and we take that to be representative of semantic similarity. So the most intuitive way of doing this, or the easiest and maybe maybe the standard also metric here, is to compute the Euclidean distance between 2 points in this vector. And to do so, what we usually do, given this equation, is compute the difference between the two vectors, and then take their norm. And the norm is basically the length. So what's the length of a vector? Is the sum of the square of its element, and then you take the square root of that. So this is, again, this part is within this equation already, right? So first we are computing the difference between the two vectors, and then we are taking the sum of the square and taking the square root. The same as points? Well, not point as in the geometrical sense, but point as in data point. Yes, so if this, so data points are represented as vectors. So, and the vector in this case would have 2 points, right? Or would have 2 values on 2 dimensions, right? Yeah.
Yeah, just to clarify that the sum in the DAE vector, then it has just n dimensions, so in that case it would be n would be equal to 2.
Yeah, exactly.
Yeah.
So that's the general sort of equation.
And you mean like the index of A and B? I was just wondering why you put the vector sign over them, because it would just be like the index,
Mm.
like in the two-dimensional, it would be x and y. Or
Yeah. Yeah. So this is just that to say that when you subtract the vectors, you have to be looking at the same so the values on the same dimension, right? So AI and BI. So you say, so in this case you subtract the x from the x and the y from the y. And so yeah, so this is pretty intuitive way of doing computing distance between vectors. But this intuitive way and simple way is actually it comes with problems. So it's simple, but it has some problems. So maybe I won't start with this. Maybe we take a break and then we come back at 1/4 and sort of not to stop within the sort of middle of it. Yeah. Have a question? Yeah. Okay. Then we'll be back at 1/4. Let's start again. So just before the break, we talked about this intuitive and easy way of measuring distance, which is the measuring similarity using the Euclidean distance. And I said that this simplicity comes at a price. And so if you look at this example here, if we assume that the vector A here represents the word automobile, and B car, and C road, and then that if we assume that the distance between A and B is 10 and B and C is 7. So does this make sense to you, or do you think there's something off here?
yeah, I mean the dimensions in each word could be different, correspond to different words, right?
Uh,
The first word in the automobile vector could be, I don't know, road, and the first word in road could be helicopter, for instance. I don't know.
no, so the dimensions here is not automobile or car word, right? So the dimensions could be sort of say passenger and drive.
Do the words have to be the same in all the vectors?
Yeah, we assume that here. They don't necessarily have to be, and they are actually not they don't always occur on the same context as you just said. But we assume this here just to show that there is a problem here, and the problem is, as you can see, is that the distance between the vector A, which is automobile, and B is actually higher than the distance between it's higher than the distance between A and C, or B and C. And it should be actually A and C here, not B and C. That's a typo. So this distance here should be AC. So we're talking about this distance and that one. And it's wrong because we know that automobile and car are more similar than automobile and road, but the result of this Euclidean distance doesn't tell us this. And the reason for that is Euclidean distance is very sensitive to extreme values and length of vectors. Meaning, if the word B, which is car here, is very frequent in our text, it will it will have higher values on the 2 dimensions, right? So it will be up there. And if automobile is infrequent, is rare, then it will be in this section, which means that the measurement or the judgment of the similarity between the 2 words is affected by frequencies. And what we want is we want our vector space model to be resilient to this side effect, which is frequencies. So as vectors of course with different frequencies will tend to have different length, the frequency will affect the similarity judgment, and that's an effect that we don't want. But we can fix this. What we can do is we can reduce all vectors, or all to reduce this frequency effect. We can normalize all of our vectors. So, and by normalizing a vector, we mean transforming it to the unit length. So all vectors would have a length of 1. And this is very simple to do. You can do that by dividing all the elements, or each element within a vector, by the length of that vector. And so if you think about that, this will always sum to 1. So for each vector, for all vectors x, for each element within x, divide that by the length of x, and then suddenly all of our vectors would be pointing to the so-called unit sphere, or in this case unit space circle. Sorry. And then now if we look again at A and B, they are actually now closer to each other than B and C, or A and C. But we can also measure similarity, or semantic similarity, in terms of proximity rather than distance. So there we're talking about this distance here, but what we want to do now is to look at the angle between the vectors. And this is much more resilient now. This will not be affected by the length of the vector. So we compute similarity as a function of the angle between the 2 vectors here. So, and that is done by computing the cosine between A and B, and the computation is simple. So you take the dot product of the 2 vectors, which is basically multiplying all of their elements, and divide that by the multiplication of the norms, or the length of the 2 vectors. So this is how we compute the cosine. And a property of the cosine function is that this the value of this equation, if you want, will be always between 0 and 1. And when 2 vectors are perpendicular, so like this, then the cosine would be when 2 vectors are perpendicular, or could you 0 exactly. And when they are pointing in the exact same direction, or they have the same orientation, that would be 1. That's and also another aspect of the cosine function is that that's what we try to say here: as the angle between the vectors shortens, the cosine approaches 1. So the cosine function decreases monotonically when the angle increases. That's the idea. But of course, here, if you want to be very precise, we have to define the range of the angle. So the range is from 0 to 90, and that makes sense for us because our space is limited to positive numbers, right? So we don't have negative numbers, so we don't care about angles that are more than 90. So we would be limited on this side and that side. And so yeah, as I mentioned, this looking at the angle would help us get sort of avoid these length bias, as they are called in this here. Sort of this length bias is inherent problem in Euclidean distance, but it doesn't do anything here. It has not, because we are looking at the angle. But we might want to still actually normalize our vectors. We might want to keep our vectors all to the unit vector, because for a simple reason. So if you look back at this equation here, we are dividing by the length of the vectors, right? So if these are 1, so A is 1 and B is 1, then we are dividing by 1, right? And so suddenly our cosine measure is basically just the dot product. Yeah, that's something also you will be doing in the assignment. So you'll be normalizing vectors sort of to the unit vector, and then applying cosine similarity using dot product. And that you will realize that this is very easy to implement and also very efficient. But another important feature that comes out of normalizing normalizing our vectors to unit vector is that when we apply cosine similarity or Euclidean distance, then we will be getting the same relative rank. Meaning that if we have a task that is give me the top 10 most similar words to car, the rank of this list would be the same whether we use normalized cosine similarity or normalized vectors in cosine similarity or Euclidean distance. Now the absolute values, sort of the similarity itself, is different. These are two different measures. But the rank, and that's what matters to us, the way they were ranked, is the same. Is this clear? So this is also a very important similarity measure that is also widely applied in many different tasks. So now if we move towards more practical sort of comments on vector spaces, and this would also help you on your assignment a little bit. Conceptually, you could think of a space or the vector space as a matrix. And that matrix has, or it's usually called co-occurrence matrix or word context matrix. So because that the dimensions in this the dimensions in our vector space are represented as columns in the matrix, and the feature vectors are the rows. So if we have m words and n features, then we would have m by n co-occurrence matrix. So let's assume this is our corpus here, and then we are looking at automobile and car, and also cars. Assume that we have done some lemmatization, so car also will fall off here. So these are the columns, which also correspond to the dimensions of our vector space, and these are the feature vectors, which represent the words that we are looking at. Right? Can you see what can you tell about this matrix, and especially about the feature vector of automobile? Yeah. Yeah, so that's an important sort of also easy way to introduce. Yeah. Exactly. Yeah. So that's a term we will introduce on the next slide. So so what you just said is that car and automobile, they occur in different contexts, but our feature vector or our vector space has dimensions for advise, avoid, and capacity and carry, etc. And these have the value of 0 for automobile, because automobile didn't occur with these words in the same context. And therefore, we have these zeros here, and our matrix will have so many zeros. So as we move towards more realistic setups, our corpus is no longer just 3 sentences. It will be, we'll talk about 1 million words, and 50,000 dimensions. So you can imagine, you can easily imagine that not all words occur with all contexts. So each new word gives rise for new dimensions, but these dimensions can maybe only occur with this word. It doesn't have to occur with any other words, which means that the number of non-zero elements within our vectors will be very low. And also this applies to our matrix, to a co-occurrence matrix. And this could be said otherwise, is that there are few active features per word. So you have a 10,000 dimension, which means you have 10,000 features. But for a given word, you might see only 100 active features, and the rest would be zeros, because this word has never occurred with the rest in your space, or the rest of the features. And this is what we call sparse features. Vectors, sorry, and sparse matrices also. So matrices that have very high, a very high number of zeros. This observation is very important because this will have implications on the way you implement your sort of the way you implement the data structure and vector operations. And that's something we have, you also have to work with on the exercise. So you don't want to choose a representation that wastes space on zeros, because they don't make any they don't introduce any meaningful aspect of the context to a given word, right? So you want to only represent the word, the vectors for a given word that have non-zero value. Have you thought about this already? Have you started working on the sort of exercise too? And yeah, so this is probably something you have already thought about, and you know what's. I won't tell you what would be the data structure to use, of course. But this also has implications on the way we implement vector operations. So, in theory, you could just look at the formulas that we used for cosine and Euclidean norm, and take them as pseudocode and translate that directly to Lisp. So you have this sum, sine, the sigma. You translate that into loop, and you just basically can do that if you want. But the question is, again, our feature vectors are sparse. So do we want to do that? Do we want to iterate over vectors that we know have many zeros, or is there a better, more efficient way to do that? That's also one thing you want to think about while you are implementing this these similarity measures. And yeah, so this is what I just said, that we don't want to iterate over all n dimensions for each vector. And yeah, that's basically the same thing. Yeah. So these were sort of notes on the implementation. Maybe we'll have time by the end of the lecture to, if you have questions about the assignment itself, but we can talk about that later. But now let's go back to the way we represented our feature vectors. So we said we want to compute co-occurrence frequencies. So we look at how many times a feature could occur with our target word, and we record that to be within our feature vector. But these are not the most discriminative, and therefore not always the best indicators of relevance. So raw frequencies, just counting how many times two words occur together, need not necessarily be the best way to measure relevance. So imagine that we have some features recording information about the direct object, and we have collected the following counts for the noun wine. So we see in our corpus that wine was the direct object of the verb buy 14 times. So that feature has the value 14. And pour 8. And so, but what we can say here immediately when we look at these two verbs and wine, we can say that maybe buy is not actually the most indicative feature of the semantics of wine, because you can buy so many different things, right? So you can buy houses, and you can buy things online, etc., etc. So, but there are fewer things that you can actually pour, right? And so our co-occurrence raw frequencies, they actually give more weight to buy because it occurs more, and that's not what we want. We wanted to give more weight to things that give us more discriminative aspects of the word wine. So to solve this, we could weight so the counts. So we do our counts. We count how many times words co-occur together. But then we can use so-called association functions to normalize these frequencies. And by normalization, we mean we want to measure whether these co-occurrences happen by chance or they were actually there is some information, mutual information between the words. I won't go into the details of this because this will sort of what we usually do, so just very broadly, we say the null hypothesis is that these words occur by chance together. And we want to apply some statistical tests to reject the null hypothesis, meaning that if these words are actually not occurring together by chance, then we want them to be given a higher sort of weight, if you want. But these functions rely on basic probability theory concepts that we will introduce in 3 weeks. So we'll just skip them, and of course we will skip them in assignment 2A. So far we have been talking about word similarity or vector spaces for word similarity. But as I said before, it's a general algebraic model that is used in for different applications. So it's not only about word similarity, and it's actually, as I said, also it takes root in IR, in information retrieval. So we can use or vector spaces are commonly used actually for finding documents with similar content. So that's what you usually do when you search online, right? So you write a query and then you want to get a web page that's similar to the query. We can use vector space models to represent documents and to represent queries. So each document is represented by a feature vector again, and this time the features are all the terms occurring in this document. So the document here is the equivalent of the word. Remember, before we were talking about word, about bread being our feature vector, our row in the matrix. This time we're talking about documents, not words. And again, spatial distance, sort of Euclidean distance, or spatial proximity, cosine similarity, more or less correspond to similarity in content. Sort of if words are, if the document feature vectors are close in our vector space, then they have maybe also similar content. And the query itself, when you search, is also represented as a vector. And the relevance of a document would be given by the distance to that query. So this is how search engines usually work. So to come back to this topic of not using raw frequencies to weight our vectors, we can look at this is a simpler TF-IDF measure, which is basically also the most the most famous maybe weighting measure or weighting function in IR. And the idea here, we don't want to use just raw frequencies. We want to assign weights to terms happening in documents. So TF-IDF stands for term frequency inverse document frequency. So TF, which is the term frequency, is basically the number of times a given term I occurs within a document dj. That's as simple as that. So it's basically just counting how many times a word occurs in a document. IDF, it's as I said, it's inverse document frequency. So we start with document frequency. What's a document frequency? It's the total number of documents in the collection that the term TI occurs in. So how many documents within our collection? So say we have 1 million documents, and we want to compute how many times TI occurs within these documents. And then based on this definition of document frequency, we define inverse document frequency, which is defined as the logarithm of n, being the total number of documents in our collection, over the document frequency. So basically, this is why we call it inverse document frequency. And you can see here is that the idea with this whole weighting function is that when a word occurs in one document and doesn't occur in the rest of the document, that's a very important word for us. But when a word occurs in one document and occurs in the rest of the documents as well, so if a word has a document frequency n, so meaning that it occurs in all of our documents in the collection, so the division here is n over n, which is 1, and the logarithm of 1 is 0. And then when we multiply this, the TF IDF would be 0, because this is not important. It's like a word, it's like a definitive article, for example. That you will see in all documents, and you don't want that to have a high weight. It will have a very high occurrence frequency, but when you apply this measure, and then it will have a 0 occurrence frequency. Sorry, not occurrence frequency. It will have a 0 weight. So to compute or to weight a given term in a document, we would apply this TF IDF here, which is basically multiplication of the term frequency within the document by the inverse document frequency. And so, as I said, a high TF IDF is obtained if a term is highly frequent or has a high frequency in a given document and a low frequency in the document collection. So over the 1 million documents, this term occurs 2 times, but within the document that we're looking at, it occurs 20 or 30 times. This is a very important term. And so the weights, in this case, even if you don't apply stop word removal, the weights themselves will filter out common terms. So you don't need to do that result. Is this clear? It's not the very, so this is not our focus in this course, of course, but it's important to know the relation between the different applications of vector spaces. You have any questions on this? Okay, so so I guess we'll have time now to answer your questions in terms of the sort of the assignment. So if you have questions, so that you can ask them now. So we're concluding. So what we have learned today, hopefully, is that word meanings can be represented as a vector characterized by n dimensions. And the n dimensions of our vectors, or our feature vectors, represent the contextual features that we observe. We said that raw co-occurrence counts are good, but maybe not the best way to quantify relevance. And semantic similarity can be computed based on spatial distance and proximity. So spatial distance, Euclidean distance, and proximity, cosine similarity. We need to be careful when deciding on a data structure to represent the co-occurrence matrix and when we implement our vector operations. So we will easily see our dimensions explode as we see more data. The more data we see, the more dimensions we have, and the more zeros we have in our matrix. And we want to be careful about this aspect. Yes, so I think I'll have time now, so that if you have looked at assignment or exercise 2A, we can discuss it now if you want, so that you don't wait until Monday to start working on it, or if you haven't started working on it yet. And these would be sort of, yeah, and these are the topics for next week. So next week we'll be looking at classification, so computing neighbor relations in semantic space, and how we represent classes, and how we represent classes, class membership, and then we look at classification algorithms, the k nearest neighbor classification, and CMEs. So yeah, I'm here for questions, I guess. Yeah.